Hello everyone. Today let's solve the problem number 100, same tree. So you can just go through the question here and you can try to understand the question with the help of example. I'll just summarize the question so that it will be easier to understand. So we are given the roots of two binary trees. You can clearly see here we are given the roots of two binary trees P and Q. We need to determine whether these two trees are exactly same. We need to determine whether these two trees are exactly same. They have given the figure here, right? So two binary trees are considered same if they have the same structure. One thing is, one condition or one requirement here is they should have the same structure. If two binary trees are considered same, if they have the same structure, they should be having the same structure and their corresponding node values are equal. Their corresponding node values has to be equal as well. These are the two requirements of the conditions that we need to remember. We need to keep this one in mind. So here you can clearly see structure is same, and also here the node values. Here you can clearly see here the structure is same and the node values are also identical or same here 1 1 2 2 3 3. So the output they have given here is true. Let's go to the example 2 here. So here the structure itself is different. So here we have the left subtree and here we don't have the left subtree. Instead we have null here. We have the right subtree, but here the node values are also not identical. Here you can clearly see here we don't have the value at all, but here we have 2. This will be considered as 1 2 null. This will be considered as 1 null 2. So yeah, this is just considered as 1 2 and this will be 1 null 2. So that's what they have given here. Now, if we consider this one, this will become 1 2 null, right? So this is fine. The output has to be false here. This is fine. So here the structure is same. We can clearly see the structure of the tree is same, but the node values differ here. 1 1 instead of 2 here we have 1. Instead of 1 here in this place we have 2, right? So the node, the value of the node are value of the nodes are not identical in this case, in the third example. So the output will be false, right? So we need to remember these two things. One is two binary trees are considered same only if they have the same structure and their corresponding node values are equal. This we need to keep in mind. So initially what we'll do, let's discuss the approach and then let's discuss the edge cases and then finally write the code and discuss the complexities of the code that we have written. Initially, as usual, let's discuss the approach. So let's discuss the approach step by step. I'll just explain it over here itself. So approach that we'll be going here is either recursion or you can consider recursive DFS. So we'll be going with the recursive DFS or the recursion here. So what is the base condition here? If both P and Q, suppose we are considering this one P, this one as Q, right? As they have mentioned in the question. So if both P and Q are null, suppose if they don't have any value at all, no elements at all, so it is empty, then we will return true, right? That is one condition. That will be base condition here. If both P and Q are null, then what we will do? We will return true because both are empty. If only one of them is null, suppose if P is null and Q is having some value, suppose let's consider only this node exists in the Q and we have 1 here, but P doesn't consist any value, consist of any element, it is null, then it will be considered as false, right? So if one of them is null, we will be returning false because one tree exists while the other doesn't, right? I hope this is clear. This is the base condition. Next, let's go with comparing the node values. So if the value of the P is not equal to value of the Q, then we will be returning false. Here you can clearly see value of P here is 1, first node, root node is 1, here also it is 1. Suppose if we have this one, we will consider 3 instead of 2. Here we have 2. So the value of 3 is not equal to 2 here, right? So we will be considering false in that case. In this case, we have 2 and 2. So it will be considered true itself, 3, 3. So all the nodes in this tree are identical to the right one, right tree, right? So we have got true here. This is one condition. We have to compare the node values. Then let's come to the third part. We will recursively compare left and right subtrees. That's what. So we'll be recursively comparing left and right subtrees. Means if both left and right subtrees are identical, if both left and right subtrees. So this is right subtree, right? If both this one. If both left and right subtrees are identical, then only we will be returning true. Then only we have to return true. Otherwise, we'll return false. So this is the approach that we will be going with. I hope the approach is completely clear. Now let's discuss the edge cases one by one and then write the code. So let's discuss the edge cases one by one. First one is for empty trees. So I'll just consider here P empty and Q also empty here. The output will be true here because we have already discussed this one. Both the trees are empty, so they are identical. So output will be true in this case. This is for the condition empty trees, right? Let's move on with the second edge case. So second edge case, we'll be discussing about the different structure. So while I say different structure, let me consider here 1, 2 and Q, let me consider here 1 null 2. So that's what the same thing they have given in the question as well. So 1, 2 will be in this way. 1 null, 2 will be here in this way, right? These are not same structured as well as the value differs here, right? So the value of the nodes are not identical. So this will be considered as false here. The output will be false because here node values differ at some position. So the structure are different, right? So let's move on with the third edge case. I'll just come here. Third edge case, different values in corresponding nodes. This is for this one. Let me write this one here. Different structure. This is for the condition different structure. So let's move on with the third condition. So different values in corresponding nodes. Different values means let me consider different values here. 1 to 1. So let me consider Q here. 1, 1, 2 here, right? So this is fine. Output will be false here. Why the output will be false here? Because node values differ at some positions. Here you can clearly see this one will be 1, 2 and 1 and this one will be 1 Q. This is P and this one will be 1, 1, 2. So this is Q. This is same as example 1, right? So this one node values differ here. You can clearly see this is same. This is different and this is also different here. So the output will be false in this case as well. This is for the condition different values in corresponding nodes. Let me give here different values in corresponding nodes here. This is fine. This is for the third edge case. Let's move on with the fourth edge case or the final edge case. Both trees are exactly same. When I say both trees are exactly same, I'll just give here. Let me consider 1, 2, 3 and Q also let me consider here 1, 2, 3. So here P will be 1, 2, 3. Q will also be 1, 2, 3 here. This is fine. All the nodes are identical and the structure is also same. So the output will be true in this case. This is for the condition both trees are exactly same. Exactly same, right? I hope this is completely clear. We have discussed all the edge cases or 4 edge cases. First one was for the empty trees. Second one was for different structure. So third one was for the different values in corresponding nodes. And final one or the fourth one was for both trees are exactly same. I hope all the edge cases are clear. Next, let's start writing the code. So let's start writing the code here. As we had discussed in the approach, initially let's go with the base case. Nothing but if both trees are empty, they are same. How can we articulate that one in the form of code? We can write in this. Yes, if not of P or not of Q, then we will return P equals q. So this is fine. Next, if node values are different, then we have to return false. If structure is same, then still if the node values differs, then we have to return false in that case, right? So how can we write that? I'll just give here, if value of p is not equal to value of q, nothing but q dot val, we can just return false in this case. This is fine. The final step is here. We have to recursively check the left and right subtrees. So we have to check all the right and subtrees recursively, right? So that's what we'll be writing in this line. So let me copy this one, as we are making use of the recursive function here. So we have to recursively check for left and right subtrees, right? So here this will be p dot left and q dot left. So this is for the left. We have to check for the right subtree as well. So I'll just include here right as well. So let me copy paste the same thing. Let me give here p dot right. Here also let me give q dot right. So this is it for the code. I hope the solution is completely clear. Let me run this one. So this is giving us wrong answer, right? So let's check what is wrong here. So here what mistake I have done here is I have added here not. I don't know why. So this one we are just checking if the value of the p not equal to q dot value of the q, right? So why did I add not symbol? I don't know. This is still fine. Let me format this one and hit the run button. So now you can clearly see the sample test cases are getting passed here, right? So let me hit the submit button now. So you can clearly see all the test cases are getting passed here, right? So the code works absolutely correct. So let's quickly discuss the time complexity and the space complexity of the code that we have written. So here the approach that we went with here is this one, recursive DFS or recursion, right? So what will be the overall time complexity here? The overall time complexity would be here big O of n. Why the overall time complexity here is big O of n? Because we are traversing the each node once. As we are making use of the recursive stack or the recursion, we are traversing each node once here, right? And what would be the space complexity here? The overall space complexity would be here big O of n as well. Why space complexity here is big O of n? Because we are making use of the recursive stack space in the worst case, that is nothing but the skewed tree. So this one space complexity would be big O of n here, right? So I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.